A completely different way to organize the address translation process is to create so-called inverted page tables. Here, the page table entries contain information, one for each element of the physical memory. So for instance, if we're thinking about physical frame numbers, each of the page table elements will correspond to one physical frame number. Today, on the most high-end platforms, we have physical memory that's on the order of tens of terabytes, whereas the virtual memory of an address space can reach petabytes and beyond. Clearly, it will be much more efficient to have a page table structure that's on the order of the available physical memory versus something that's on the order of the virtual memory that a process can have. To find the translation, the page table is searched based on the process ID and the first part of the virtual address, similar to what we saw before. When the appropriate PID and P entry is found into this page table, the index, the element where this information is stored, that will denote the physical frame number of the memory location that's indexed by this logical address. So then that is combined with the actual offset to produce the physical address that's being referenced from the CPU. The problem with inverted page tables is that we have to perform a linear search of the page table to see which one of its entry matches the PIDP information that's part of the logical address that was presented by the CPU. Since the physical memory can be arbitrarily assigned to different processes, the table isn't really ordered. There may be two consecutive entries that represent memory allocated to two different processes. And there really isn't some clever search technique to speed up this process. In practice, the TLB will catch a lot of these memory references, so this detailed search is not performed very frequently. However, we still have to perform it periodically, so we have to do something to make it a little bit more efficient. To address this issue, inverted page tables are supplemented with so-called hashing page tables. In most general terms, a hashing page table looks something as follows. A hash is computed on a part of the address, and that is an entry into the hash table that points to a linked list of possible matches for this part of the address. So that allows us to basically speed up the process of the linear search to narrow it down to few possible entries into the inverted page table. As a result, we speed up the address translation.